morning, ladies and gentlemen, here to the technical forum of our group exhibit Hydrogen Fuel Cells and Batteries. We're coming now to our second presentation this morning. Also a gentleman from Norway from the same booth, which is D62. And I would like to announce you Dr. Guttorm Syvertsen-Wiig. He is product manager at CerPoTech AS. And he will talk about the impact of raw material quality on performance and energy applications. Please enter the stage. This is your hand.
Thank you. Okay, so I'm Guttorm Syvertsen-Wiig, coming from another Norwegian company. And we're producing oxide materials for energy applications, among others. So I just give an introduction to the company and say a few words on our our technology, what we do, how we produce our powders, and then give a few examples of materials and performance in comparison with other materials in the end. So, what are we? We consider ourselves as a toolbox for ceramic oxides, and anyone in need of some functional materials for a number of applications can come to us, and we'll work together to develop the best materials for their need. So we're a spin-off company based on technology. When in 2003, a research group at the Norwegian University of Science and Technology in Trondheim figured out that it was difficult to obtain materials with good quality and in large quantities and so on. So they decided to set up their own production line, a spray pyrolysis unit. And then over the years, their partners and friends was interested in this powder, and they didn't have the capacity to produce this when doing their own research, so they founded a company. And since 2007, we've been located in the basement of the university with a lot of drawbacks, with students coming in and out, a lot of rooms, limited space, and so on. So we got some venture capital and investors last year, which made it possible for us to move out from the university and set up our own pilot plant facility. So what we do is spray pyrolysis based on aqueous precursors, meaning we're dissolving different elements in water and then mixing them again and spray to get powder. And these are typically custom-made materials for a number of purposes I'll come back to. So just a comparison on making powders in your garage and in a nice facility is before we had a capacity of a little bit less than 100 kilos per year. Now, just by moving and scaling a little bit up in both ends of the production, and the technology is essentially the same. We can now produce up to 5 tons per year. And also the batch size is quite important, especially when going to the industry and so on, that for research purposes you need maybe 1 kilo, but then scale up you need 100, 200 and so on. And this is we can do easily now. And also we have more control on the quality, so the consistency between each batch is much higher. And of course the price drops dramatically when you go up in amounts. And this process is actually, you don't need to go higher than 2, 3, 4, 5 kilos until you really see the economy of scale. So what can our materials be used for? Here at this Hanov Messe, it's mostly solid oxide fuel cells focusing around. So we are making different cathode materials, anode materials, electrolyte materials, and so on. But also ceramic membranes, mixed ionic electronic conductors, proton conductors, and also lately we've been focusing a bit on batteries, especially cathode materials, but also novel solid-state electrolytes. So we're going to join a few proposals at least, and hopefully projects later on. And also we have had some own activity on lead-free piezoelectrics, which is a hot topic since lead is banned by the EU, but we still don't have materials that perform as good as the lead-containing materials, so it's still allowed. And a lot of other applications such as sensors, oxide thermoelectrics, catalysts, LEDs, TCOs, and so on. So as long as you need a functional oxide, we can give it to you. So the core technology is the spray pyrolysis, which I explained briefly, that we dissolve the precursor ions in a water-based solution. We standardize this, and then we mix them together, so we very carefully can control the stoichiometry of the material, which prevents secondary phases and so on. In this solution we spray into a hot furnace, and then the powder of water evaporates, and you collect the powder in the end. So it's a lot of the know-how lies in the solution stabilization, but also thermodynamics on how to achieve phase pure powders. And we also work with other synthesis routes on a small scale, but that's not what's the most interesting. So there's a schematic on what's happening during the spraying and pyrolysis. You first have an atomized droplet of solution which evaporates, so you have a metal shell, eggshell-like structure. This decomposes partially in the furnace into metal oxides and some carbonates, maybe some nitrates left, which means we had to use another thermal treatment to decompose all the material. Then you get a very homogeneous ceramic powder after deagglomeration or milling down these hollow spheres. And the typical size of these materials are, the spheres are 5 to 30 microns, and particles 100 nanometers to up to 1 micrometer. Then most importantly, you have very small crystallites, which give rise to both catalytic activity and so on, but also very high sintering activities. But all these numbers depend very much on which material you're working on. So we have our own periodic table of elements. All these green elements here are elements that we are used to work with, and we can combine these into many different compositions and materials. We also can work with some more of these, for instance silicon and phosphor, but for strategic reasons we have avoided this so far, especially because ionic conductors, which we have been working a lot with, are very sensitive to silicon impurities. For instance, will ruin the properties. But now we have the possibility to have our own equipment for this. So what the main benefits, or our benefits, we say, is the flexibility. We're tailor-making materials from all these different elements. So we have between 50 and 100 different materials we have made over the years. Here's just a list, so you have a understanding of how many, and it's even more than this. Another important thing that is often forgotten is that when you work in a lab and you find it's great material, it works super. But the problem is you can only make 10 grams or maybe 1 kilo per day, and that's not viable when you're going to scale up in the end anyway. So we're making batches down to about 300 grams and up to as big as you want, basically. So you can work with the same material from day one as you will in the end when commercializing your final product. And also we can do screenings with different doping levels quite easily in the same process. And also we have developed a new technique to make very fine composites, very finely dispersed, for instance as anode for SOFCs. And also we can provide slurries and inks and also sputtering targets. As I said, we're making very homogeneous powders due to the process. The phase purity is very high because we're controlling the stoichiometry very well. And the level of contaminations is also quite small. Of course, that depends on how much you're willing to pay, because for some elements the 99.9 and the next 9 is quite expensive. Also, it's for the industry, maybe the most important point is the sinterability of the powder, because it means you can reduce the processing temperature. Also, when you have other components, that will be quite important. And we have a narrow size distribution. And also due to this, I mean, you see an image of the particles, and you have a very high surface area combined with that it's not particles broken down, but it's the surfaces. It's quite often very active catalytically. And also we are a quite academic company with a lot of competence. We still have access to all the infrastructure at the university and are collaborating quite closely with professors there. And we've been partner in 5 European projects under the 7th Framework Program. 2 of these are fuel cell, or 3 of these are fuel cell projects. METPROCELL and EFIPRO on proton conducting fuel cells. EVOLVE on conventional solid oxide fuel cells with a optimized anode, and DEMCAMER, which is everything surrounding gas, and AMS Copper is a project on coatings for door knobs and such, which are killing bacteria. And also we have had some own activity in a national project on lead-free actuator components. So just a couple of quick examples and comparisons. Our Sinter, it's a research institute in Norway, did a benchmark test of the CerPoTech powder with co-precipitated powder from another supplier. It's lanthanum nickelate. And as you see, first of all, the CerPoTech powder is more phase pure. It's the red one on the bottom, and you have some impurities in the other powder. And sinterability is quite important. I mean, the onset of sintering is shifted 150-200 degrees, and also the sintering activity is much higher for spray pyrolyzed powder compared to the co-precipitated powder. And in the end, the performance on this was an oxygen separation membrane, so it's much higher flux from the membrane made by our materials for a number of reasons. One is sintering temperature. Also, you have some impurities that might affect grain size. Of course, is important, and which also can affect the surface modifications. Another example is a cathode material, comparing 2 materials made by solid-state synthesis with the CerPoTech powder. So the ASR is significantly lower. And also here it's a number of reasons why this could be. You have the phase purity, the grain size, conductivity could be different, secondary phases, and so on, and the density of the triple phase boundaries. This is the results actually from the EVOLVE project we're a partner in. And the final example is another electrical conductive material where the CerPoTech powder is very much performing better than powder made by solid-state synthesis. This, of course, also could be related to the phase purity and the grain size, but also thermal history is an important factor to consider, because in many materials you have it could be challenging to obtain the correct structure because you have several polymers that are kinetically stabilized. So just to sum up, the starting materials do matter. One composition is not necessarily the same composition if it's produced in another method. And the microstructure is affected by morphology of your powders and thermal treatments and so on. And also the final point here, that scalability should always be considered when aiming for a final product in the end, which I guess most research is all about. So thank you for your attention, and you can stop by our Norwegian booth. It's D62 if you're interested to have some more information. Thank you.
Yeah, thank you very much, Dr. Syvertsen-Wiig, for this excellent presentation. Are there any questions from your side so far? Well, maybe I may have the first question. So, as I understood, this is material used in SOFCs. That's correct. Yeah. We've just heard the presentation from ZEG. Do you sell your materials to ZEG?
No,
not yet.
they don't make the cells.
They make it
We're
themselves.
at the bottom of the value chain. All right. We have to deliver to the guys making the cells.
Right.
And then they either make the stacks or sell it to someone making the stacks, which again, selling to someone making the system, and then someone implementing the whole thing. So.
Okay, but inside there's your material, isn't it? In the end.
It could be.
You don't know really. Okay. Very good.
I know that's not our material, but.
Yeah. Well,
it should be.
We talk a lot about hydrogen and fuel cells and waiting for real market introduction to sell it in large scales. Could you scale up your product as high that you can really provide the economy with a lot of this powder?
Yeah, it's in principle it's a very scalable process, and we're operating in a batch-to-batch mode. But in principle, you can run this continuously. Which means that you're limited by one thing is the solubility of your precursor materials, because it takes longer to pump through that amount of liquid, and also post-processing, but everything can be scaled, and then you can just get another production line, which is the investment cost is not very big.
And the raw materials are not restricted, like platinum is, for instance.
Most are controlled by the Chinese as always, but
they still sell it.
Yeah, we don't decide on which materials to work with. Our partners and customers we want this, and we provide it to them. But we have felt the rare earth price increase a couple of years ago.
All right. Are there any more questions from your side? And I would like to thank Mr. Syvertsen-Wiig for his presentation and for taking the question. Thank you very much once again. Ladies and gentlemen, next presentation will be here in the Technical Forum at 11 o'clock. I see the speaker already there. There's Professor Stephen Bennington, CEO at Celler Energy Limited, and he will talk about safe, low-cost hydrogen storage. So please stay tuned, have a seat, have a drink on the house, and wait until 11 o'clock when this presentation will take place here in the Technical Forum. Thank you very much.